Hello and welcome back to Class Online. So, the topic in front of us today is energy and chemical reactions. Energy and chemical reactions. So, when we did chemical reactions, we said that we have what is called decomposition reaction, where a compound is broken down into its constituent parts. That means the bond in the compound is broken, and then the different parts that made up that compound is broken out and it's separated. And in chemical reactions, when bonds are broken, energy in the form of heat is absorbed. And then we also say we have addition reaction, where different elements can combine to form a compound. And so in chemical reactions, when if chemical elements combine to form a compound, a bond is formed. And when bonds are formed in chemical reactions, heat, that's energy in the form of heat, is released. So the breaking down of bonds leads to the absorption of heat, energy, while the formation of bonds lead to the release of heat energy. So you see, heat energy is what we refer to as energy now in chemical reactions. So the topic, energy and chemical reactions. Now, due to this absorption of energy when chemical bonds are broken and the release of energy when chemical bonds are formed, chemical reactions almost always involve a change in energy between products and reactants. So we're going to use the law of conservation of energy to see how to deal with these energy changes. So the law of conservation of energy states that the total energy of a system must remain unchanged, and that oftentimes the chemical reactions will absorb or release energy in the form of light, heat, or both. So we're going to use this law to govern this topic. Now, the energy change in a chemical reaction is due to the difference in the amount of stored chemical energy between the products and the reactants. Now, this stored chemical energy or heat energy of a system is what we call enthalpy. So we may be calling energy change enthalpy change. So the stored chemical energy in the reactants or the products is what is called enthalpy. Enthalpy or heat content. Enthalpy is the same thing as heat content. Alright, so we're going to look at some reactions that take place, and the ones that involve heat, the one that involve light and heat, the one that involves sound and heat. Just take a little examples before we go on. Now, when a strong acid and a strong base are mixed, heat is released. Acid and base combine to form a neutral substance, so heat is released. So that kind of reactions will have energy in form of heat alone. Now, when magnesium is burned in air, light and heat is evolved. So not just heat now, light and heat is evolved. But then when a mixture of hydrogen and oxygen is ignited, sound and heat is evolved. Remember, pop sound. So sound and heat is evolved. So now, of these energy changes, we can only measure the changes in heat energy with ease. So of all these heat energy, light energy, sound energy, we can only measure the heat energy easily. Others are difficult to measure. So we're going to be dealing with this of heat alone. The energy change that accompanies a chemical reaction is known as the heat of reaction. And the unit for measuring heat change is the kilocalorie, which is defined as the amount of heat needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. So the implication is that 1 kilocalorie is equal to 1000 calories. So 1000 calories make 1 kilocalorie. Okay. Now, since heat is a form of energy, the unit used for measuring heat change is also the joule. So we can also use joule. And mathematically, 1 kilocalorie is the same thing, is equal to 4.18 joules. So if we approximate that, 1 kilocalorie will be equal to 4.2 joules, and that's the standard. So 4.2 joules of heat is required to raise the temperature of 1 gram of water by 1 Kelvin or 1 degree Celsius. And therefore 1 joule is the energy required to raise the temperature of 1 gram of water by 0.239 Kelvin or degree Celsius. So you see that is written in underline, so take it seriously. You can see it in your exams. Now we have two types of reactions when we deal with heat. We have the exothermic reaction and we have the endothermic reactions. Okay. Exothermic, as the name implies, involves release of heat. So heat is released. So exothermic reactions release heat and light into their surroundings. Example, in combustion reactions, you see, it's exothermic because heat is released. If you burn firewood, burn whatever you're burning, heat is released. You feel that hotness. Now, in exothermic reactions, the products have less enthalpy. Remember, enthalpy is heat energy. So the products have less enthalpy, less heat energy than the reactants, because the products give up heat, that's enthalpy. And as a result, an exothermic reaction is said to have a negative enthalpy of reaction. It's losing the heat, negative. This means that the energy required to break the bonds in reactants is less than the energy released when new bonds form in these products. Excess energy from the reaction is what is released as heat and light. So that's exothermic reaction. Primary thing there is that exothermic reaction involves release of heat and light. So enthalpy is negative. Good. Now, endothermic reaction is the opposite of exothermic reaction, where exothermic reaction releases heat. Endothermic reaction will be absorbing heat. So endothermic reactions absorb heat and light from their surroundings. For example, decomposition reactions are usually endothermic. So you can have this at the tip of your fingers. Decomposition reactions usually will be endothermic, but combustion reactions always will be exothermic. So, and in endothermic reactions, the products have more enthalpy than the reactants. The products are gaining more energy, absorbing more heat. So it has more energy, more enthalpy, heat energy, more enthalpy than those of the reactants. Thus, an endothermic reaction is said to have a positive enthalpy. Positive enthalpy. This means that the energy required to break the bonds in the reactant is more than the energy released when new bonds form in the products. So in other words, the reaction requires energy to proceed. The reaction requires energy to proceed. In the decomposition of water into hydrogen and oxygen, for example, when water is heated to over 2000 degrees Celsius, a small fraction will decompose into hydrogen and oxygen. A small fraction. Significant heat energy is needed, say about 285.58 kilojoules, is needed for this reaction to proceed. So you see, that's an example of endothermic reaction, because the reaction requires energy to proceed. So you get that. Okay, so let's use this knowledge for energy changes. Heat content is represented by delta H. Delta means change. You know that sign, like a triangle. So delta H means change in heat. The H is heat. So since the change in heat content during a reaction is the difference between the heat content of the products and that of the reactants, then change in heat should be expressed mathematically as heat content of product minus heat content of reactants. So you see delta H will be heat content of products minus heat content of reactants. Now take very good note of this. Change in heat is negative for exothermic reactions. So remember we said that enthalpy change is negative for exothermic. That's because it's losing heat to the environment. So change in heat is negative for exothermic reactions, whereas change in heat is positive for endothermic reaction. Now let's see the kinds of heat reactions that can take place. We have a lot of them. We have heat of formation, we have heat of neutralization, we have heat of combustion, we have heat of solution. So we're going to discuss them one by one and see what happens when a bond is formed. What happens when a combustion reaction takes place? What happens when a neutralization reaction takes place? What are the different heats and how does it work? Energy changes. How does it work when this kind of heats are produced or this kind of reactions are taking place? So we start with heat of formation. Heat of formation. The amount of heat evolved or absorbed when a substance is formed is known as the heat of formation, or you call it enthalpy of formation. The standard heat of formation of a substance is the heat evolved or absorbed, that is the enthalpy change, when 1 mole of that substance is formed from its elements under standard conditions. Under standard conditions. Now take note. The formation of water vapor requires less energy than the formation of liquid water. I'll repeat that. The formation of water vapor, water in gaseous state, requires less energy, that is minus 241 degrees Celsius. Minus 241 joules, while the formation of liquid water just needs minus 258. So if you calculate the difference, that is a change in heat. Remember we said that change in enthalpy is a difference between the heat content of the product and that of the reactant. So if you calculate the change in heat of these two, water vapor and the liquid, which turns to vapor. So the liquid is the reactant, the vapor is the product. So okay, so if you subtract 258 from 241, you have 44. So the change in heat is 44. Example, we take note of this. The equation for formation of 1 mole of liquid water is as follows. Okay, so H2 plus half O2 yields H2O, and the change in heat is minus 285.58. You can see that in the book there, and take notes. Just look at the equation and then you'll understand better. So that's heat of formation, and you measure the amount of heat evolved, given off, or the amount of heat absorbed, taken in when a substance is formed. Then that is the heat of formation. And we have taken example with water vapor, water in a gaseous state, and then water in a liquid state. All right, so let's look at heat of neutralization. You remember when we said titration reaction is a very good example of neutralization reaction, where see an acid reacts with a base to become a neutral substance. So neutralization reaction will be having heat of neutralization. Let's look at this. Neutralization is an exothermic reaction. So that you've heard that already means it's going to be giving out heat, losing heat. The amount of heat evolved, given off, during a neutralization reaction is in which 1 mole of water is formed is known as the heat of neutralization. Whenever you see heat of, you can also replace it with enthalpy change. Heat change, enthalpy change. I'm not going to repeat that. So we call it enthalpy change of neutralization. The standard heat of neutralization is the amount of heat evolved when 1 mole of hydrogen ions from an acid reacts with 1 mole of hydroxide ions from an alkali, a base, to form 1 mole of water under standard conditions. Under standard conditions. Alright. Please take note of this. If it's not visible in your notes, please make it very visible. The formula for total heat evolved is mass times specific heat capacity times temperature rise. Mass times specific heat capacity times temperature rise. Let's look at that example so you can solve problems concerning heat of neutralization. Given that for the reaction KOH, potassium hydroxide, plus HCl, hydrochloric acid, KOH is the base, the alkali, HCl is the acid, so this is a neutralization reaction. KOH plus HCl yields KCl plus H2O, and the change in heat given in the question is minus 54 kilojoules per mole. Now you're asked from that equation, what is the quantity of heat evolved in the reaction? So you are being asked for heat of neutralization, the enthalpy change of neutralization. Now remember that enthalpy change of neutralization, that's heat of neutralization, is the amount of heat evolved when 1 mole of H plus ions from an acid reacts with 1 mole of OH ions from the base to form how many moles? 1 mole of water. 1 mole of acid reacts with 1 mole of base to form 1 mole of water. Now, if we look at that, our question, we have 1 mole of KOH. Okay, sorry, that question was not complete. I said, given that for the reaction KOH plus HCl yields KCl plus H2O, and the change in heat was minus 54 kilojoule per mole. And you're asked, what is the quantity of heat evolved in this other reaction I'm going to read now? 2NaOH plus H2SO4 yields Na2SO4 plus 2H2O. Now, I'll reread that question. You're given 2 moles of sodium hydroxide, that's the base, the alkali, combining with 1 mole of sulfuric acid to yield sodium sulfates and 2 moles of water. But in the first equation, which you are to use to compare with this, you were given KOH, 1 mole of potassium hydroxide, combining with 1 mole of HCl, hydrochloric acid, to yield 1 mole of potassium chloride and 1 mole of water. So everything was just 1 mole. And the enthalpy of neutralization says that the amount of heat evolved when 1 mole of the acid reacts with 1 mole of base to form 1 mole of water. Now in the equation you are given, we have 2 moles of base and we have 1 mole of acid, but then we have 2 moles of water formed. So that means that 2 moles of the base plus 1 mole of acid that reacted to form 2 moles of water would be 2 times the the heat content, the enthalpy change that should be formed, because we're not having 1 mole of the water formed now, we're having 2 moles. That means the enthalpy change is doubled. So if the enthalpy change when 1 mole of acid reacts with 1 mole of a base to form 1 mole of water is minus 54 kilojoules per mole, then if 2 moles of a base react with 1 mole of an acid to form 2 moles of water, then the enthalpy change of neutralization will no longer be 54. It will be 2 times 54 because now 2 moles of water is formed. So if you calculate that, since everything was in negative, 2 times minus 54 kilojoules, and then you have your enthalpy change of neutralization to be 108, that's negative, minus 108 kilojoule per mole. So that's how to calculate questions, problems on heat of neutralization. So we've seen heat of formation, we've seen heat of neutralization. Now we're looking at heat of combustion. Heat of combustion. Now the amount of heat evolved. Remember, combustion reaction is always exothermic reaction. So the amount of heat evolved when 1 mole of a substance is burned completely in oxygen is known as the heat of combustion, or enthalpy change of combustion, brothers and sisters. Heat of combustion, enthalpy change of combustion. Same thing. Okay. The standard heat of combustion of a substance is the heat evolved when 1 mole of the substance is burned completely in oxygen under standard conditions. Under standard conditions. Under standard conditions. Now, the determination of heat of combustion is carried out with a bomb calorimeter. So the instrument used in determining the heat of combustion of a reaction is the bomb calorimeter. Bomb calorimeter. And let's also see an example how to calculate heat of combustion. See example, given that the standard heat of combustion of butane as C4H10 is plus 5877 kilojoule per mole, calculate the heat of combustion of 14.5 grams of butane. We already know that the molar mass of a compound is the mass of that compound represented in gram per mole. Mass is in gram, but molar mass is gram per mole. If the mass of a compound is 10, the molar mass of that compound is 10 gram mole. So it's just the molar mass is the mass, but represented in gram mole. So you know that C4H10, if you want to calculate the molar mass, will give you 58 because C is 4. 12 times 4. You add that to H, since H is 1. So that means 10 of H will be just 10. 1 times 10. So C, which is 12. 12 in 4 places gives you 48. Plus 10, which is 58. That means the mass of butane is 58 grams. But the molar mass of butane is 58 gram mole. You understand that? So if the molar mass of if 58 grams as the mass of butane yields 58 gram mole, so that's the molar mass. Okay, so we can use that to find the heat of combustion when 4.5 grams of butane is reacted. So that would be the heat that was given the standard heat of combustion of butane there multiplied by the gram, that's the mass of the butane that is actually reacting, divided by its molar mass. So that is 5877 multiplied by 14.5 grams of the butane divided by the molar mass of butane, which is 58, to give you 1469.25 kilojoules. So that's a simple way of solving that one. Another fast one, calculate the heat change when 60 grams of carbon undergoes complete combustion to produce carbon dioxide. You know, C is 12. So this one, you see, if you write out the reaction, you see carbon reacting with oxygen to produce carbon dioxide, and the enthalpy change is minus 3935 kilojoule per mole. Now the question is, what's the heat change, what's the enthalpy change when 60 grams of carbon is the one undergoing this combustion reaction? Okay, so you know 1 gram of carbon is 1 mole of carbon is 12 grams. So it's left for us to say, okay, if 12 grams of carbon has the standard enthalpy change of minus 39.35, that means 60 grams of carbon will evolve minus 39.35 times 60 divided by 12. And then if you do that, you see that you have minus 19675 kilojoule per mole. Alright, so now we see heat of solution. Heat of solution, we say enthalpy of solution. When an ionic solid dissolves in water, a two-step process occurs. Now, each of these steps is accompanied by heat change. So, these steps are, number one, the water molecules will split up the ions in the crystal into free ions. So, the solid ions now are now broken down and they can move. So, they are free ions. Now, this process needs energy known as lattice energy. This crystal was in the lattice, we call it crystal lattice. They were bonded, so you need lattice energy to break down those bonds and make the ions free. So that's the first step. So number two, the second step, the free ions are then hydrated by water molecules, soaked up. This process involves energy known as hydration energy. So we have lattice energy, which is needed to break down the crystal form of the ions into free ions. And then we have hydration energy, which is the energy evolved when ions are hydrated by water. Alright, now the resultant heat energy of those two steps determines whether the dissolution is exothermic. So it is known as the heat of solution. The heat of solution is the enthalpy change associated with the dissolution of a solute in a solvent, solute like salt in a solvent like water, at constant pressure, resulting in dilution. So you dilute when you put in water, you understand that. Now, the standard heat of solution is the amount of heat absorbed or evolved when 1 mole of a substance is dissolved in so much water that further dilution would result in detectable heat change. Take notes. 1 mole of a substance is dissolved in so much water that if you further add that water, then you will visibly detect heat change. That's standard heat of solution. Take note of this again. Dissolution is exothermic if the lattice energy is less than hydration energy. Remember what lattice energy and hydration energy are. So dissolution is exothermic. Remember we said that the resultant heat change of these two steps determines whether the dissolution is exothermic or not. So dissolution is exothermic if lattice energy is less than hydration energy. But dissolution will be endothermic. So dissolution is endothermic if the lattice energy is greater than the hydration energy. If I would want to explain that more, remember lattice energy is the energy needed to break down the crystal form of the ion to free ions. So if this energy is less than the energy it takes, the energy evolved when the free ions are absorbed, then that dissolution is exothermic. But if the lattice energy, that's the energy needed to break down the crystal form into free ions, is greater than the energy evolved when the free ions are hydrated, then the solution is endothermic. I think that's the best I can do here. Alright, so in hydrated salts, where the ions are already hydrated before dissolution, the total heat of hydration would be very small. So we have less heat of hydration now. Hence, the solution of hydrated salts is endothermic because we have the lattice energy is greater now than the hydration energy. So that's a very good example I've given you. Now let's look at this lattice energy in comparison with bond energy and lattice energy. Energy changes in chemical reactions are due to the formation, there's the forming and breaking of bonds. So the strength of a particular bond is usually measured by the amount of energy required to separate the atoms or ions held together by the bond. So this is known as the bond energy. So the bond energy is the strength, as the amount of energy required to separate atoms or ions that are held together by a bond. That's the bond energy. So this is the energy that is absorbed when a particular bond is broken. The bond energy is what is absorbed or evolved when a bond is formed. The bond energy evolved when a bond is formed, and that's absorbed when a bond is broken, are the same only for homonuclear molecules. Homonuclear molecules, molecules from the same atom, hydrogen with another hydrogen, H2, same atoms form a molecule. Chlorine with chlorine forms Cl2, homonuclear, the same atoms forming a molecule. But they are slightly different for heteronuclear molecules. Now, hydrogen forming a molecule with chlorine, they are not the same atoms now, different atoms, but they form one molecule. So take note that the bond energy evolved or absorbed will be the same if the bond is in a homonuclear molecule, but slightly, a little bit different if it's a heteronuclear molecule. All right, so listen to this. Bond energies help you also to understand the stability of molecular or what? Covalent substances. Molecules or covalent substances. Molecules, molecular or covalent substances. But then lattice energy helps you to understand the stability of ionic crystals. Ionic crystals. What's the difference? Ions out here for lattice energy, and then molecules, covalent substances for bond energy. So you see the comparison now. The lattice energy of an ionic crystal is the heat of formation of 1 mole of ionic compound from widely separated gaseous ions under standard conditions. Under standard conditions. All right. Now, before we proceed, we want to look at something important. Spontaneous and non-spontaneous processes. I know in the course of teaching you have mentioned spontaneous reactions, which are reactions which will tend to happen without obstruction. And non-spontaneous will not happen except an extra force is applied. So we're going to see these processes, spontaneous and non-spontaneous processes. A spontaneous process is capable of proceeding in a given direction without needing to be driven by an outside or external energy. So you don't need an external force to drive a spontaneous reaction, a spontaneous process. Now, they proceed when left to themselves, and in the absence of any attempts to drive them in reverse. Like I used the example in the class, you keep a round ball, uphill. It tends to, roll down. Without you pushing it, it will roll down. But you want to roll it up back there, you have to carry it there, or you push. Now let's see other examples of spontaneous processes. A smell diffusing in a room. Do you stop that? It happens on its own. Spray a perfume on one end of the room. No, you don't need to stop it. At the other corner of the room, it will diffuse to that part. So that's a process that is spontaneous. It happens without obstruction. Another one, ice melting in lukewarm water. You put ice that is ice cold into water that was not as cold, that is not as cold as the temperature in the refrigerator. The ice will start melting because of the little heat it's gaining. Starts, melting. You can't stop it except you take it off and put it back in the fridge. Salt dissolving in water. I bet you can't stop that also. It will happen. Except you try to reverse it by stopping the salt and drying it, But as long as it keeps being inside the water, it will dissolve. So it's a spontaneous process. And also iron rusting. As long as that iron is outside and water and air and sun is hitting it, touching it, it will rust. Slowly, but it will rust. So those are examples of spontaneous processes. Now, most exothermic reactions, most hexagonic reactions. So now I'm calling exothermic hexagonic. Same thing, in your exams you may be seeing exothermic, but I'm just giving you hexagonic in case you see it in future. You won't be shocked. No, it's not hexagonic, it's exothermic now. So most exothermic or most hexagonic processes occur spontaneously. Remember, exothermic processes occur spontaneously due to the decrease in the overall enthalpy of the system. Exothermic reactions give out energy. So the energy in the system, the enthalpy in the system keeps decreasing. Because of this, it's spontaneous, because it will just keep losing, it will keep happening, going that way. Some endothermic, some endagonic. So endothermic, endagonic, same thing, whereas exothermic, hexagonic. So some endothermic or endagonic processes, however, can also take place spontaneously. Example, the crystals of ammonium triazonitrate 5 will dissolve spontaneously as it absorbs so much heat. So thus, enthalpy is not the only factor that determines the spontaneity of a process. We have other factors. So that a process happens on its own accord. It is not just determined by if it's exothermic or endothermic. That's not just the only factors. Other factors include entropy, the entropy of the system, and the free energy. So we're going to look at this entropy, and then what's free energy? Now, entropy has a symbol S. Entropy is a property of a substance that is a measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. That is unavailable for doing useful work. Or simply you say entropy is the measure of the degree of disorder or randomness of a substance. So a perfectly ordered system at 0 Kelvin has an entropy of 0. So as temperature increases, the degree of disorder, degree of entropy, the entropy increases, degree of disorder, entropy increases. However, increase in temperature alone has little effect on entropy. Entropy increases greatly when solids melt and liquids vaporize. When solids melt and liquids vaporize, entropy increases greatly. So it's not just the temperature. Temperature even has very little effects on entropy. So entropy increases greatly when solids melt and liquids vaporize. When a reversible chemical change occurs at a constant temperature, the change in entropy is equal to the heat absorbed or evolved. So you see now, temperature is constant, so the entropy is equal to the heat absorbed or the heat evolved. And so when that happens, we have change in entropy to be change in heat all over temperature. That's the absolute temperature. Change in entropy is change in S. I told you entropy has a symbol S. So change in S means change in entropy. And the formula is change in entropy is equal to change in heat, change in H, all over T. That's absolute temperature at which the process occurs. Alright, if heat is absorbed, change in entropy, change in S, is positive, and there is an increase in entropy. But if heat is evolved, change in entropy is negative, and there is a decrease in entropy. So we've seen entropy, and now let's see free energy. Free energy has a symbol G, capital G. The free energy of a chemical system is that energy which is available for doing work. Entropy is that temperature that is unavailable. The thermal energy that is unavailable for doing useful work. Now, the free energy is that energy that is available for doing work. This is the driving force that brings about a chemical change. So, changing entropy, you want to derive free energy from change in entropy. So total change in entropy is equal to the change in entropy of the surroundings plus the change in entropy of the system. But you know that change in entropy of the surrounding is equal to is minus change in heat all over absolute temperature. So if that happens, that means change in entropy, total change in entropy will be minus change in heat over total over temperature, absolute temperature, plus change in entropy of the system. So we're just replacing the alternate formula for change in entropy of the surrounding. So you see the same thing. So if you multiply through by T, the absolute temperature, you see that T change in entropy, the T change in absolute T change in the total entropy is equal to minus change in heat plus T change in entropy of the system. Or if you reverse, if you bring out, if you change the negative sign out, bring out the negative sign. So you have minus change in entropy, total entropy, equal to change in heat minus T change in entropy of the system. You get that? So the quantity, that quantity minus T change in total change in entropy is called the free energy. So if you look at that, we brought it out now. We brought it out, say, or minus T change in total entropy. That's minus T change in total entropy is what we call free energy, and you use the symbol change in G since free energy is G. So we can call this whole part of it that says minus T change in S total, we just call that change in G since it's the same thing as free energy. So that means if you look at that equation that said minus T change in S total equals to change in H minus T change in S system, and if you want to rewrite it using minus TAS total as change in G, you can say change in G equals to change in H minus T change in S of the system. That's change in entropy of the system. Or you simply say change in G, that's free energy or Gibbs energy, is equal to minus change in total entropy change. So that's the formula for Gibbs energy. Change in Gibbs energy, change in free energy. Change in free energy equals to minus T change in entropy, total change in entropy. All right. Now, for a chemical change to occur spontaneously, the total change in entropy must be positive, as the total entropy must increase. Now, since free energy, change in free energy is minus T change in total entropy, therefore change in entropy, total change in entropy, therefore for total change in entropy to be positive, change in free energy must be negative. So that means for all spontaneous changes, change in free energy must be negative. Take note of that. If you don't understand any other thing I've been explaining in this formula of free energy, for all spontaneous changes, change in G, that's change in free energy or change in Gibbs energy, must be negative. If change in G is positive, the reaction will not take place, because we say it must be negative. So listen to why it must be like that. Unless some condition is altered to make change in G negative, change in G must be negative. So if it's positive, it will not work, except you alter some things to make change in G negative, then that reaction takes place. So how do you alter to make it negative? Usually by supplying heat to the system. That's raising the temperature of the system. So if change in G is 0, then the chemical system is in a state of dynamic equilibrium, state of equilibrium. This happens when both change in heat and change in entropy are negative or positive. When negative and negative multiply through or add up, becomes positive. 0. So when both change in heat and change in entropy are negative, or they are both positive, then you're going to have change in Gibbs energy, change in free energy as 0. And when that happens, say the chemical system is in a state of equilibrium. Alright, so as a summary of the topic, energy and chemical reactions, I would say that a spontaneous reaction is a reaction that occurs without being driven by an external force. So a non-spontaneous reaction would not occur except an external force drives it. And then I will say there are some conditions that could make a reaction spontaneous. Now, if a reaction wasn't spontaneous, there are some conditions that could make that reaction spontaneous. One of them being that the Gibbs energy must be negative, and then the entropy must increase. Alright, so that's the end of the topic here. Energy and chemical reactions. Do well to gather up your questions and ask. Alright.